What if everything you thought you knew about the universe was only a fraction of the story? Picture a reality where black holes don't just bend light, they erase information from existence. A cosmos where time itself can flow backward under certain conditions, and where the fundamental laws of physics seem to contradict one another in the most spectacular ways. This isn't science fiction. This is the actual frontier of human knowledge, a place where the universe reveals its deepest, most bewildering secrets through what scientists call cosmic paradoxes. These are not errors in our math or flaws in our logic. They are glaring signs that there is so much more to learn, and that reality is far stranger, more layered, and more mysterious than we ever dared to imagine. From the unsettling silence that makes us question whether we're truly alone in the universe, to the quantum riddles that suggest our very observations might shape the fabric of existence, each paradox will explore cracks open a door to a new way of seeing everything. We're going to journey through 22 of these mind-bending concepts, each one a collision between what we expect and what actually is. Some emerge from the immense scales of astrophysics, where dark energy pushes galaxies apart faster and faster, defying all prediction. Others arise in the subatomic realm, where particles seem to communicate across time and space, challenging our understanding of cause and effect. What ties them all together is this: they force us to rethink not just the rules, but the very nature of reality itself. This video is an invitation to step into that uncertainty, to wander through the questions that even top physicists and cosmologists are still grappling with. There are no simple answers here, and that's what makes the journey so thrilling. You might find yourself re-examining what it means to exist, to observe, and to be part of a universe that is constantly revealing its complexities. So settle in, open your mind, and get ready to explore the enigmas that don't just puzzle scientists, they reshape our entire understanding of space, time, and everything in between. Remember, some of the most profound discoveries begin not with an answer, but with a really good question. But to truly appreciate the strange and beautiful contradictions we're about to explore, it's helpful to understand where they come from. These aren't just random brain teasers, they are the inevitable growing pains of human knowledge. For centuries, the greatest minds have stumbled upon these puzzling inconsistencies, and each time, they've been forced to tear up the old map and draw a new one. Think of Aristotle wrestling with Zeno's paradoxes about motion, or the revolutionary shift when Copernicus placed the sun at the center of the solar system, directly contradicting the evidence of our own eyes. Every major leap in understanding began with a paradox that refused to go away. In our modern era, the most profound paradoxes erupt at the boundary between our two most successful and stubbornly conflicting theories of reality. On one hand, we have Einstein's general relativity, which masterfully describes the cosmos on the grandest scales, the warping of spacetime by gravity, the dance of galaxies, and the very expansion of the universe itself. It paints a picture of a smooth, continuous, and predictable cosmic fabric. On the other hand, we have quantum mechanics, which rules the realm of the impossibly small. It reveals a world that is granular, probabilistic, and wildly unpredictable, where particles can be in two places at once and seemingly communicate faster than light. Independently, both theories are stunningly accurate, but when they meet, like trying to force two puzzle pieces from different boxes, they create chaos and contradiction. They speak different mathematical languages and obey different rules. A black hole, for instance, is an object so massive that it demands general relativity to describe it, yet it is so small that quantum mechanics must apply. This violent clash gives birth to paradoxes that signal we are on the verge of something new. They are not failures of science, They are its compass, pointing directly toward the gaps in our understanding and demanding a deeper, more unified theory of everything. Engaging with these puzzles requires a unique blend of tools. It's not enough to just be a physicist or a philosopher. You have to be a bit of both. You need the rigorous mathematics to model the universe and the deep, conceptual thinking to interpret what those models are actually saying about the nature of existence. It's a field that is as intellectually rewarding as it is humbling, constantly reminding us that the universe is far weirder than our everyday experience would ever suggest. So as we begin our countdown, remember that each paradox is more than a riddle, it's a beacon, guiding us toward the next great revolution in our understanding of everything. So we begin our journey into the cosmic unknown with perhaps the most famous and deeply personal paradox of all, one that touches on our very desire for connection in a seemingly infinite universe. The numbers are absolutely staggering. Our galaxy alone contains over 100 billion stars, and many of these are now known to host their own families of planets. With recent telescope data, we've learned that rocky, Earth-like worlds orbiting within the habitable zone, where liquid water can exist, are not rare exceptions but could be incredibly common. When you extend this view to the 2 trillion galaxies in the observable universe, the statistics become almost incomprehensible. The sheer probability seems to scream that we should not be alone. The cosmos should be a vibrant, noisy metropolis teeming with life and civilizations. And yet, when we train our most powerful radio telescopes on the heavens, when we scan the skies for any sign of artificial signals or engineering on an astronomical scale, we are met with a profound and unsettling silence. This glaring contradiction between the high probability of life and the complete lack of any proof is the heart of the Fermi Paradox, named for the physicist Enrico Fermi who, over a casual lunch in 1950, famously asked, "Where is everybody?" It's a question that has only grown more urgent and more haunting with every new exoplanet we discover. The silence isn't just a scientific puzzle, it feels like a message, and interpreting what that message means forces us to confront some truly profound possibilities about life, intelligence, and our own future. One of the most discussed explanations is the sobering concept of the Great Filter. This idea suggests that the evolution of life from simple chemistry to a spacefaring civilization requires clearing a series of monumental hurdles, and at least one of these steps is so improbably difficult that it acts as a barrier that almost every potential civilization fails to pass. The terrifying question for us is whether that filter is behind us or still ahead. Is the Great Filter something like the origin of life itself, or the jump from single-celled to multicellular organisms? If so, then we are an incredible fluke, a cosmic lottery winner in a universe mostly empty of company. But the more chilling possibility is that the filter lies in wait for us in our future. Perhaps the development of advanced technology like artificial intelligence or nuclear weaponry inevitably leads to a civilization's self-destruction. The silence we hear, in that case, could be the echo of countless other civilizations that reached our level of development and then vanished. Other theories are less apocalyptic but no less mind-bending. It could be that space is just too vast, and the timescales involved are too long for civilizations to overlap in a meaningful way. Imagine an advanced species that flourished and went extinct 100 million years ago. Their radio signals now dissipated into a faint whisper lost in the background noise of the universe. Or perhaps they are out there, but their technology and consciousness are so advanced that they are utterly unrecognizable to us. We might be like ants crawling across a highway, completely unaware of the complex civilization of beings that built it. They could be communicating in ways we haven't even begun to imagine, using neutrino streams or quantum entanglement, making our search for simple radio waves seem primitive. This cosmic silence ultimately holds up a mirror to humanity. The Fermi Paradox forces us to question our assumptions, our uniqueness, and our longevity. It reminds us that the absence of evidence is not evidence of absence, and that the search itself is an act of profound hope. Every new effort, from SETI to the JWST, is an attempt to answer this fundamental question about our place in the cosmos. Are we a miracle, a cautionary tale, or simply late to the party? The paradox doesn't give us answers, but it gives us the most important thing of all, a reason to keep looking up and wondering. But if the silence of the cosmos makes us feel lonely, the next paradox threatens to unravel the very fabric of reality itself, based on a principle so fundamental it's practically sacred in physics: information cannot be destroyed. Think about that for a moment. If you were to burn a book, the ashes and smoke might seem like a chaotic mess, but in theory, if you could track every single particle, every bit of energy and its trajectory, you could perfectly reverse the process and reconstruct the book. The information about its words, its ink, its binding, it all still exists, just in a different, more dispersed form. This isn't just a quirky idea, it's a cornerstone of quantum mechanics. The universe, it seems, is the ultimate archivist, never deleting a single byte of data about what everything is and where it has been. Now bring a black hole into the picture. A black hole is the universe's ultimate shredder. Once matter crosses that point of no return, the event horizon, it is lost to us forever, crushed into an infinitely dense point called a singularity. According to Einstein's general relativity, that information is gone, trapped inside and permanently severed from our universe. For decades, this was just a strange but accepted feature of these bizarre objects. Then along came Stephen Hawking, who made a stunning realization. He discovered that black holes aren't completely black. Due to weird quantum effects happening right at the edge of the event horizon, they slowly leak a faint form of radiation. This Hawking radiation causes the black hole to lose mass and, over unimaginable eons, evaporate completely until it just vanishes. And here lies the catastrophic problem. Hawking radiation is thermal. It's random and featureless, like the heat radiating from a stove. It doesn't seem to carry any of the specific information about the stars, planets, or books that fell in. So when the black hole finally evaporates, all that unique information appears to have been erased from existence. Poof, gone. This creates the black hole information paradox. Quantum mechanics says information must be preserved, but black holes plus Hawking radiation seem to destroy it. It's as if the universe's archivist has a giant paper shredder that leaves no trace, violating a fundamental law of physics and creating a crisis that has divided theoretical physicists for half a century. Hawking himself initially believed the information was truly lost, which would have meant rewriting quantum mechanics. This idea was so unsettling that it led to a famous bet with fellow physicist John Preskill, who argued information must somehow be preserved. The debate forced physicists to propose wild, mind-bending solutions. Perhaps the information isn't lost but is encoded on the surface of the event horizon itself, a concept known as the holographic principle. In this view, everything that falls into a three-dimensional black hole is smeared like a perfect, two-dimensional hologram onto its surface. The information is never actually inside the black hole. It's painted on its outer boundary, and it's slowly and subtly imprinted onto the Hawking radiation as the black hole evaporates. Another radical idea is that black holes don't have a singularity at their center at all, but that our understanding of gravity breaks down before that point, preventing the information from being truly destroyed. Resolving this paradox is more than an academic exercise. It's likely the key to unlocking a theory of quantum gravity, a framework that can finally marry the law of the very large general relativity with the law of the very small, quantum mechanics. The fate of information falling into a black hole might just be the thread we need to pull to unravel the deepest secrets of the universe, revealing a reality that is even stranger and more interconnected than we ever dreamed. But while the black hole information paradox takes us into the realm of the deeply theoretical, our next enigma begins with something far simpler: the simple, beautiful darkness of a clear night sky. It seems so obvious, so natural, that we rarely stop to question it. Yet, in the early 19th century, the German astronomer Heinrich Wilhelm Olbers asked a deceptively simple question that would eventually crack open our understanding of the entire cosmos. If the universe is truly infinite, unchanging, and filled with an endless number of stars, then every single line of sight we have when we look up should eventually land on the surface of a star. Imagine a dense, endless forest. No matter which direction you look, your gaze will eventually be stopped by a tree trunk. In an infinite, static universe, the night sky should not be dark at all. It should be a blinding, uniform sheet of starlight, as bright as the surface of the sun. The fact that it isn't the fact that we see blackness between the stars is Olbers' paradox, and its resolution is one of the most important clues we have about the history of everything. For a long time, proposed solutions fell short. Some suggested that dust clouds in space must be blocking the distant starlight, but this doesn't work. Over immense amounts of time, that dust would absorb so much energy that it would heat up until it glowed just as brightly as the stars themselves. The true answer is far more profound and tells a dynamic story of a universe with a definite beginning. The key is that the universe is not static, and it is not infinitely old. We live in an expanding cosmos that burst into existence a finite time ago. This means two incredible things. First, because the universe is only about 13.8 billion years old, there hasn't been enough time for light from stars beyond a certain distance to ever reach us. Our observable universe has a horizon, and we cannot see beyond it because the light from those regions hasn't had time to travel to our eyes. Second, and perhaps even more mind-bending, is the effect of this expansion on the light that is traveling toward us. As space itself stretches, it pulls the light waves along with it, causing them to lengthen. This phenomenon is called redshift. The farther away a galaxy is, the faster it appears to be moving away from us, and the more its light is shifted toward the red, and eventually the infrared part of the spectrum. For the most distant objects, their light is redshifted so dramatically that it falls completely outside the range of visible light, becoming invisible to our eyes. The energy is still there, but it has been transformed into a form we cannot see, contributing to the faint glow of microwaves that fill all of space, the cosmic microwave background radiation, the ancient afterglow of the Big Bang. So the darkness between the stars is not a void, it is a historical record. It is filled with the faded, stretched light of the early universe, telling us a story of a cosmic birth and a rapid, ongoing expansion. Olbers' simple question, born from looking up at a seemingly empty sky, directly led to the development of the Big Bang theory and fundamentally changed our place in the cosmos. We are not in a timeless, eternal universe, but a dynamic one with a history, a beginning, and likely, a future that is still being written. The night sky is dark precisely because the universe had a starting gun, and we are still listening to the echo. Now, let's bring these cosmic puzzles a little closer to home with a paradox that literally hits home, the twin paradox. Picture two identical twins. One is an intrepid astronaut who boards a state-of-the-art spacecraft capable of flying at a significant fraction of the speed of light, perhaps 90%, on a journey to a distant star and back. The other twin stays firmly planted on Earth, living a normal life. According to Einstein's special theory of relativity, time for the traveling twin will pass more slowly than for the stay-at-home twin. When the astronaut returns after what felt like a few years, they step out of the ship to find their Earth-bound sibling has aged decades. The traveler is now dramatically younger. This isn't science fiction. It's a direct prediction of the well-established physics of time dilation, where motion through space directly affects the passage of time. The paradox isn't in the aging difference itself, but in the apparent symmetry that seems to break it. A core principle of relativity is that all motion is relative. From the astronaut's perspective, couldn't you argue that they are stationary while the Earth and their twin fly away from them at near light speed and then return? If that were true, then the Earth twin should be the one who is younger upon reunion. You can't have it both ways. The situation seems logically contradictory. This is the heart of the apparent paradox. It forces us to look deeper and realize that the two twins' experiences are not, in fact, symmetrical. The key difference is acceleration. The twin on the rocket doesn't just move at a constant velocity. To turn around and come home, the spacecraft must slow down, reverse direction, and accelerate again. This period of acceleration is absolute. The traveling twin feels genuine G-forces. They are pushed back into their seat in a way that the Earth-bound twin never experiences. It is this acceleration that breaks the symmetry and definitively tells us which twin is truly in motion, for the purpose of calculating time dilation. This stunning prediction is far more than a thought experiment. It has been confirmed repeatedly with incredible precision. We may not have human twins traveling at relativistic speeds, but we have the next best thing: atomic clocks. In a famous experiment in 1971, scientists flew incredibly accurate atomic clocks on commercial jetliners around the world. When compared to identical clocks that remained on the ground, the traveling clocks were found to be ever so slightly behind. The difference was tiny, mere billionths of a second, but it was there, exactly as relativity predicted. This effect isn't just a laboratory curiosity. It's a critical correction that must be programmed into the GPS satellites orbiting our planet every single day. These satellites are moving at high speeds relative to the Earth's surface, and the signals they send are also affected by the planet's gravity, another factor that warps time. If the engineers at Mission Control didn't constantly adjust the satellite clocks for these relativistic effects, the entire GPS system would become useless, accumulating errors of several miles within just a few hours. The profound implication of the twin paradox is that time is not the universal, constant tick of a cosmic clock that Newton imagined. It is a flexible, malleable dimension, intimately woven together with the three dimensions of space into a single fabric called spacetime. Your personal experience of time, how quickly or slowly it passes, depends entirely on your path through this four-dimensional reality. Your speed and your proximity to gravitational fields like planets or stars will literally shape your future. This forces us to completely abandon our intuitive, everyday notion of a single, objective now. There is no privileged frame of reference. There is only your personal journey through the block universe of spacetime, and that journey is unique to you. The twin paradox is a gateway to understanding that the universe is far more strange and wonderful than it appears, a place where the flow of time itself is a personal experience, not a universal decree. But our journey through the bizarre now takes us from the personal experience of time to a paradox that unravels the very idea of origin itself. What if you could become your own ancestor? What if a song, a scientific formula, or even a person could exist without ever having been created by anyone? This is the mind-melting realm of the Bootstrap Paradox, a causal loop where an effect circles back to become its own cause, creating a closed loop of existence with no discernible beginning. The name comes from the absurd idea of pulling yourself up by your own bootstraps, an impossible feat that perfectly captures the self-creating, self-sustaining nature of these loops. It's a concept that pushes the boundaries of logic and forces us to ask whether everything in the universe truly needs a starting point. Let's make this abstract idea concrete with a classic example. Imagine you are a huge fan of a particular symphony, a masterpiece of such beauty and complexity that it moves you deeply. You somehow acquire a working time machine, and you decide to travel back to meet the composer in the year 1750, decades before the symphony was written. Eager to share your love for their work, you present them with a perfectly transcribed copy of the sheet music. The composer is astonished. They study your gift, are utterly inspired, and then proceed to publish the symphony under their own name at the exact time it was originally supposed to appear in history. The symphony becomes the famous masterpiece you know and love, but here is the devastating question: who actually composed it? The music didn't originate with the composer, it came from you. And you got it from the composer, so where did the notes, the melody, the harmony, the information itself first come into being? It seems to have no point of creation. It simply always existed, trapped in an infinite loop with no author and no genesis. This isn't just a fun plot for a science fiction story. In the world of theoretical physics, such loops are not only possible, but are predicted by certain solutions to Einstein's field equations in general relativity. These solutions, known as closed time-like curves, provide a geometric pathway for time travel into the past within a specific region of spacetime. In these regions, the fabric of the cosmos is twisted in such a way that an object's world line, the path it takes through the four dimensions of spacetime, curves back on itself, allowing it to interact with its own past. A particle, or perhaps a person, could travel along this curve and end up at an event in their own history. If they were to pass information or even a physical object to their past self, that object would then travel forward in time again, only to be handed back. The object would have no ultimate origin. Its entire history would be a single, unbreakable loop in time. The Bootstrap Paradox strikes at the heart of our most fundamental assumptions about reality, that every event has a cause, and that cause must always come before its effect. This principle, called causality, is the bedrock of classical physics and of how we experience the world every single day. A bootstrap loop shatters this principle, presenting a scenario where the effect is the cause, and the sequence of events is a circle with no starting point. This forces philosophers and physicists to grapple with profound questions. If such loops are possible, does the concept of creation even have meaning? Could the universe itself be a bootstrap paradox, existing without a first cause? It also raises terrifying questions about free will. If you travel back in time and give Shakespeare his plays, did he ever have a choice to write them? The events seem predetermined, locked into a cycle that cannot be broken, suggesting that in a universe with time travel, freedom might be nothing but an illusion. Ultimately, the Bootstrap Paradox does more than challenge time travel. It challenges our understanding of existence. It suggests that information, ideas, or even physical objects might not need a creator. They could simply be eternally self-existent, their origins lost in an infinite regress of cause and effect. It blurs the line between discovery and invention, making us wonder if some of humanity's greatest leaps forward, a revolutionary theory, a stunning work of art, were not created at all, but rather found, unearthed from a timeline that had always contained them. It's a concept that feels inherently wrong to our logical minds, and that is precisely why it is so captivating. It reminds us that the universe might operate on a logic far stranger and more wonderful than our own. But if the idea of influencing the past with a quantum eraser seems abstract, our next paradox demonstrates a way to manipulate the present and even freeze time itself simply by looking. Welcome to the bizarre and counterintuitive world of the quantum Zeno effect. It gets its name from the ancient Greek philosopher Zeno of Elea, who proposed a series of paradoxes arguing that motion is an illusion. One of his most famous arguments, the arrow paradox, claims that at any given instant, a flying arrow is motionless in a specific point in space. Since time is composed of a series of these instants, Zeno concluded the arrow can never actually be in motion. While his logic is flawed in our everyday classical world, in the strange realm of quantum mechanics, a version of his idea turns out to be eerily correct. You really can stop a process in its tracks not by arguing about it, but by repeatedly and incessantly observing it. To understand how this works, we need to step into the quantum shoes of an unstable particle, like a radioactive atom that's poised to decay. In the quantum description, this atom isn't definitely decayed or not decayed. Instead, it exists in a fuzzy, probabilistic state known as a superposition, represented by its wave function. This wave function evolves smoothly over time, and the probability that the atom has decayed gradually increases. However, the moment you decide to measure it, to check and see if it's still there, you force its wave function to collapse. The act of measurement pins it down to a single, definite state. Either it is still intact or it has decayed. If you find it still intact, you have effectively reset its clock. The evolution of its wave function starts all over again from that point, like restarting a stopwatch. Now, if you measure it again an extremely short time later, and then again and again in rapid succession, you continuously reset the probability of it decaying back to zero. You are, in a very real sense, watching the pot so it never boils. Your persistent observation prevents the natural progression of events, freezing the particle in its initial, undecayed state. This isn't just a theoretical curiosity. It has been proven in laboratories around the world. In a landmark experiment in 1990, researchers at the National Institute of Standards and Technology used lasers to repeatedly observe or probe a group of beryllium atoms that were prepared in an excited, unstable energy state. By zapping these atoms with laser pulses at precisely timed intervals, they effectively kept measuring whether the atoms had dropped back to their stable ground state. The result was astonishing. The more frequently they made this observation, the slower the atoms were to decay. When the observations were rapid enough, the decay was virtually halted. The atoms were trapped in their excited state by the relentless attention of the experimenters. It was a dramatic demonstration that measurement is not a passive act of seeing but an active intervention that physically alters the system being observed. This effect profoundly challenges the classical, Newtonian view of the universe as a giant clockwork mechanism that ticks along on its own, completely independent of whether anyone is watching. The quantum Zeno effect suggests that at its most fundamental level, reality is responsive. It seems to require an interaction, a measurement, to actualize definite events from a sea of possibilities. This forces us to confront a deeply philosophical question: what exactly constitutes a measurement? Does it require a conscious human observer, or is it simply any interaction with another particle or the environment? The Copenhagen interpretation of quantum mechanics, pioneered by Niels Bohr and Werner Heisenberg, leans into the idea that the observer is inextricably linked to the outcome, that reality isn't fully formed until it is measured. Other interpretations, like the many worlds theory, try to remove the special role of the observer, but the Zeno effect remains a stark reminder of the power of measurement to shape reality. The implications ripple out from the lab into the realm of potential future technologies. If we can freeze the state of a quantum system by observing it, we might be able to protect fragile quantum information from degrading, a major hurdle in the development of quantum computers. This is often called quantum watchmaking, the art of using frequent measurements to keep a qubit, the basic unit of quantum information, stable and coherent long enough to perform calculations. It's a paradoxical tool, using observation, which normally causes collapse and disturbance, to instead maintain order and control. The quantum Zeno effect transforms from a philosophical mind bender into a potential engineering principle, showcasing how the deepest paradoxes of quantum mechanics might one day power a revolution in technology, all born from the simple, profound act of looking. And just when we thought we had a handle on the universe's expansion, a discovery at the close of the 20th century sent shockwaves through the world of cosmology, revealing a force so baffling it makes up most of the cosmos yet defies all explanation. For decades, the prevailing assumption was that the universe, after the initial fireball of the Big Bang, was gradually slowing down. The mutual gravitational pull of all the matter, stars, galaxies, dark matter, was thought to be acting like a cosmic brake, gently decelerating the expansion. Astronomers set out to measure this slowdown by observing distant supernovae, the brilliant stellar explosions that serve as standard candles for measuring vast cosmic distances. But what they found was the opposite. The data revealed that the expansion wasn't slowing down at all. It was speeding up. The universe, against all expectation, was accelerating apart, as if some mysterious, repulsive force was blowing it up like a balloon from the inside. This revelation was so startling and so counterintuitive that it earned the teams behind it the Nobel Prize in Physics in 2011, and the mysterious culprit was given a name that reflects our profound ignorance: dark energy. This discovery immediately created what is arguably the largest and most embarrassing discrepancy in all of science, known as the cosmological constant problem. To understand the sheer scale of this problem, we need to look at the two numbers at its heart. On one side, we have the value of dark energy's strength as measured by astronomers through its effect on the cosmos. It is a small, positive number that drives the accelerating expansion. On the other side, we have the prediction from our most successful theory of the small-scale world, quantum field theory. This theory tells us that even the vacuum of empty space is not truly empty. It is a seething, bubbling foam of virtual particles constantly flashing in and out of existence. This quantum foam should be brimming with a colossal amount of vacuum energy, and this energy should, according to Einstein's equations, act exactly like a cosmological constant, a repulsive force causing expansion. The problem is one of magnitude. The energy density predicted by quantum theory is about 10 to the power of 120 times larger than the value we actually observe. That's a 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the entire history of physics, a number so preposterously large that it would be funny if it weren't so serious. It's like theory predicting that a single raindrop should contain all the water in all the Earth's oceans, while observation shows it's just a normal drop of water. This staggering discrepancy forces physicists to consider a few deeply unsettling possibilities. The first is that there is something fundamentally wrong with our understanding of quantum mechanics or gravity when applied to the vacuum of space. Perhaps the virtual particles that quantum field theory so accurately describes in other contexts don't contribute to gravity in the way we think they do. Maybe there is a hidden symmetry or a cancellation mechanism of unimaginable precision at work, where all these enormous positive and negative energy contributions somehow balance out to almost, but not quite, zero, leaving behind the tiny remnant we call dark energy. Theories like supersymmetry, which posits a partner particle for every known particle, were hoped to provide such a cancellation, but even they don't get us close enough to the observed value. This has led many to believe that an entirely new framework of physics is required, one that can seamlessly unite quantum mechanics and general relativity into a theory of quantum gravity. The implications of this paradox extend far beyond theoretical headaches. They dictate the ultimate fate of everything. Dark energy isn't a minor component of the universe. Observations from the Planck satellite and other instruments confirm it makes up about 68% of the entire cosmos. It is the dominant force, the master of cosmic destiny. If it continues to accelerate the expansion as it is now, it will lead to a profoundly lonely future. Distant galaxies will be pushed beyond our observable horizon, their light never able to reach us again. The universe will become a cold, dark, and empty place, with islands of galaxies isolated from one another in an ever-growing void. This is known as the Big Freeze or heat death. The dark energy paradox is therefore not just an academic puzzle. It is a question about the end of all things. Solving it would mean unlocking the deepest secrets of the vacuum of space itself, revealing whether this acceleration is a constant force that will persist forever, or a dynamic field that could one day decay or even reverse, leading to a dramatically different cosmic finale. It stands as a humbling reminder that the void is not nothingness, but rather the most powerful and least understood something in existence. This vision of a cosmic end, a silent, eternal equilibrium known as heat death, is one of the most profound and sobering conclusions drawn from the second law of thermodynamics. The law tells us that entropy, a measure of disorder, always increases in an isolated system. The entire universe is the ultimate isolated system. Over trillions upon trillions of years, all the energy that currently fuels stars, powers life, and creates structure will inevitably become evenly distributed throughout the cosmos. Temperature differences will vanish. Every region of space will settle into a uniform, lukewarm bath of particles. No more stars will ignite, no more work can be done, and no more complex processes can occur. It is the ultimate fade to black, a state of maximum entropy where the story of the universe effectively ends, not with a bang, but with a whisper. For any being that values structure, thought, and existence, it appears to be the final, inescapable oblivion. Yet, just as this picture of eternal stillness seems complete, the bizarre rules of the quantum world poke a hole in it, suggesting that even in this state of perfect equilibrium, the show might not be over. Quantum mechanics teaches us that true nothingness is impossible. Even in a perfect vacuum, at the absolute zero of temperature, the fabric of space-time is never truly still. It is alive with quantum fluctuations, tiny, temporary bursts of energy where virtual particles spontaneously pop into and out of existence, borrowing energy from the vacuum before vanishing again to repay the debt. In our current vibrant universe, these fluctuations are a minor background hum, but in the inconceivably vast timescales of a heat-dead cosmos, they become the main event. Given enough time, and we are talking about time scales that make the current age of the universe look like a single blink of an eye, these random fluctuations could theoretically give rise to anything. A single hydrogen atom could appear, a complex molecule could spontaneously assemble, or, in an event of unimaginably low probability, an entire new universe could bubble into existence through a mechanism like quantum tunneling, birthing a new cosmic cycle from the ashes of the old. This creates a stunning philosophical standoff between two of physics' most powerful theories. Classical thermodynamics paints a picture of an inevitable, one-way slide into a permanent, featureless equilibrium, a true end. Quantum mechanics, however, offers a bizarre loophole, suggesting that given eternity, randomness can and will eventually recreate complexity, perhaps even an entire new Big Bang. This is the core of the heat-death paradox, the conflict between the classical arrow of time pointing toward stillness and the quantum promise of eternal, if sporadic, rebirth. It forces us to ask which theory holds the final word on the ultimate fate of all that exists. Will the universe truly achieve a final, eternal state of rest, or is it destined for an endless cycle of death and renewal on timescales so vast they defy human comprehension? This paradox has inspired some of the most creative and mind-expanding theories in all of cosmology. One compelling idea is that of a cyclical universe, or a big bounce, where the universe expands, contracts, and then explodes again in a new Big Bang, over and over for all eternity. Another, even more speculative concept is that of a quantum reset. In this scenario, a quantum fluctuation in the far, far future doesn't just create a new universe in a separate bubble, but actually causes the entire cosmos to tunnel back to a high-energy state near its beginning, effectively restarting its own timeline in a massive cosmic recurrence. Perhaps the most fascinating proposals come from thinkers who ponder the fate of consciousness itself. Could a sufficiently advanced civilization, aware of the heat-death approaching, find a way to harness these very quantum fluctuations to power their existence? They might encode their consciousness onto these tiny ripples in spacetime, existing as faint, disembodied patterns of information, processing thoughts over intervals of millions of years, persisting in a universe that to any outside observer would appear completely and utterly dead. This merges cutting-edge cosmology with deep philosophy, forcing us to confront what truly gives life meaning. Is it the grand, dramatic narrative of stars and galaxies, or could meaning be found in the sheer, stubborn persistence of awareness against an infinite backdrop of silence, finding purpose not in creating but in enduring? The heat-death paradox challenges us to think not just about the end of everything, but about the nature of everything that makes existence worthwhile. But if the ultimate fate of the cosmos lies in the far distant future, our next paradox brings the mystery shockingly close to home, suggesting that the reality you are experiencing right now might not be base reality at all. The simulation paradox begins with a seemingly simple and increasingly plausible premise. If a civilization becomes technologically advanced enough, it would likely develop the ability to create incredibly realistic, immersive simulations of reality. These wouldn't be the virtual reality headsets of today, but perfect, full sensory experiences that are utterly indistinguishable from the real world for the conscious minds within them. Now, if such a capability is possible, and if even a fraction of these advanced civilizations have any interest in running such simulations, for scientific research, historical recreation, or even entertainment, then the number of simulated realities in existence could quickly become astronomical, vastly outnumbering the one single, original, physical universe. This is where the logic takes a sharp turn into the profoundly unsettling. If there are billions or trillions of perfectly realistic simulations running, and only one base reality, what are the statistical odds that you and I are living in that one true original world? The answer is almost zero. It is far more probable that we are living in one of the countless simulations. This line of reasoning, famously formalized by philosopher Nick Bostrom in 2003, presents us with a trilemma, three possibilities, at least one of which must be true. Either one, virtually all civilizations at our level of development go extinct before achieving this simulation technology, perhaps by the great filter we discussed earlier. Or two, those that do reach a post-human stage have absolutely zero interest in running ancestor simulations. Or three, we are almost certainly living in a computer simulation. Since the first two options seem rather unlikely given humanity's current trajectory and insatiable curiosity, the third option becomes disturbingly plausible. The paradox deepens when you follow this chain of reasoning to its logical conclusion. If we are in a simulation, then the beings who created our simulation, the entities we might call our simulators or programmers, are themselves part of a reality. But what is the nature of their reality? If the technological capability to simulate reality is possible in their world, then it is just as statistically likely that they, too, are living in a simulation created by an even earlier civilization. This leads to an infinite regress, a potentially endless stack of simulations within simulations, with no clear bottom level, no definitive base reality to be found. We could be a simulation created by a simulation created by another simulation, ad infinitum. This modern twist on Cartesian skepticism, centuries after Descartes wondered if an evil demon could be deceiving his senses, uses the language of computing and probability to question the very fabric of our existence. While this idea is currently untestable and may forever remain in the realm of philosophy, it gains a certain traction from the breathtaking pace of our own technological advancement. Just look at how far we've come in a few decades, from simple text-based computer games to photorealistic graphics and immersive virtual reality that can already trick our senses to a degree. If this rate of progress continues or even accelerates with the advent of artificial intelligence, creating a fully convincing simulation seems less like science fiction and more like an eventual inevitability. This line of thought forces us to confront staggering ethical and metaphysical questions. If we are in a simulation, do our actions have any true meaning? Does the suffering or joy experienced within the simulation matter to the creators, or are we merely characters in an elaborate game? If we one day create such simulations ourselves, what ethical responsibilities do we have toward the conscious beings within them? Ultimately, the simulation paradox does more than just suggest we might be lines of code in an alien computer. It fundamentally blurs the line between creator and creation, between the physical and the digital, and between reality and perception. It invites us to look at the world around us with a newfound sense of wonder and suspicion, to question the fine-tuning of physical constants that allow for life, or the odd quantum mechanical rules that seem almost like an optimization to save on processing power. It challenges us to wonder who or what might be pulling the strings and for what purpose. Whether you find the idea terrifying or liberating, it serves as a powerful reminder that the nature of reality is the deepest mystery of all, and the answers might be far stranger than we ever imagined. This brings us to a paradox that doesn't just question the nature of reality, but the very act of looking at it. At the heart of quantum mechanics lies one of its most baffling and iconic behaviors, perfectly illustrated by the famous double-slit experiment. When you fire a stream of particles like electrons at a barrier with two narrow slits, you would expect them to behave like tiny bullets, each going through one slit or the other and creating two neat bands on a detector screen behind it. But that's not what happens. Instead, the particles create an interference pattern of multiple stripes, a signature behavior of waves. It's as if each individual electron is passing through both slits at once as a wave of possibilities and interfering with itself on the other side. This is bizarre enough, but the true magic and the source of the paradox happens when you try to watch. The moment you place a measuring device by one of the slits to see which opening each electron actually goes through, the behavior changes instantly. The interference pattern vanishes. The electrons stop behaving like waves spread out over space and start behaving like well-behaved little particles, each going through a single slit and creating just two bands on the screen. It seems the simple act of observation, of trying to pin down a definite path, forces the electron to abandon its fuzzy, wave-like existence and choose a single, concrete reality. This is the observer effect paradox in its purest form, and it forces a deeply uncomfortable question. What exactly is special about a measurement? What qualifies as an observer? In our everyday world, we assume reality exists independently of us. A tree falls in the forest whether anyone hears it or not, but in the quantum realm, this common sense notion shatters. Does the observer require a conscious mind? This was a position seriously considered by some of the founders of quantum mechanics, like John von Neumann and Eugene Wigner. In this view, it is the consciousness of a human experimenter that finally collapses the wave function, translating possibility into actuality. This idea places human awareness at the very center of the cosmic story, suggesting that the universe only becomes definite when perceived by a mind, a concept that feels more like philosophy than physics and makes many scientists deeply uneasy. The more widely accepted interpretation today is that measurement is simply a physical interaction. It doesn't require consciousness. The observer isn't a person. It's any macroscopic object, a Geiger counter, a photographic plate, or even just another particle that becomes entangled with the quantum system. When the fragile quantum state interacts with the messy, large-scale environment, its delicate superposition is instantly destroyed in a process called decoherence. The information about all the possible states leaks out into the environment, and what we are left with is a single, classical outcome. In this view, the measuring device is just another physical system, and the collapse is a consequence of interaction, not contemplation. This resolves the need for consciousness but still leaves a fuzzy boundary. When does a system become big and messy enough to count as a measuring device? Is it 2 atoms, 2000? There's no clear line, which suggests our definition of observation is still incomplete. This core dilemma has given rise to the two most prominent interpretations of quantum mechanics, each offering a radically different solution to the observer problem. The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, essentially accepts the paradox. It states that a particle doesn't have definite properties like position or momentum until it is measured. Before measurement, it exists only as a probability wave. The act of measurement is a fundamental and irreducible part of the theory, a special process that breaks the normal evolution of the wave function. It draws a sharp line between the quantum world and the classical world of the observer, but it never clearly defines where that line is. In stark contrast, the many worlds interpretation proposed by Hugh Everett eliminates the observer's special role entirely. It says the wave function never collapses. Instead, at the moment of a measurement, every possible outcome actually occurs, but each one plays out in a newly branched parallel universe. In one world, the electron went through the left slit. In another, it went through the right. The observer themselves splits, each version perceiving a different outcome and believing theirs is the only one. There is no paradox because there is no single outcome to cause a contradiction. Everything that can happen does happen across an infinite multiverse. Ultimately, the observer effect paradox pushes us to the precipice of science and into the realm of metaphysics. It challenges the deepest assumptions about an objective reality out there, independent of our interaction with it. Quantum mechanics seems to suggest that reality is relational, that properties are not inherent but are defined by the context of measurement. An electron isn't a wave or a particle. It shows one face or the other depending on how we choose to question it. This doesn't mean we create reality with our thoughts, but it strongly implies that we are participators in a cosmic dance, where the questions we ask inevitably shape the answers we receive. The universe may not be a pre-written script but an improvisational performance, and we, through our experiments and our observations, are writing the lines as we go along. But our journey through the bizarre now takes us from the quantum realm of observation to one of the most famous and enduring thought experiments about time travel, a paradox so deeply personal it strikes at the very heart of our own existence. Imagine you've finally done it. You've built a fully functional time machine. Your first destination isn't to see the dinosaurs or to glimpse the future, but something more intimate. You want to meet your own grandfather as a young man long before he started a family. Perhaps it's out of simple curiosity, but something goes terribly wrong during your visit. In a moment of pure accident, you cause his untimely death before he ever has a chance to meet your grandmother. The immediate, horrifying question arises: if your grandfather dies before fathering your parent, then you could never have been born. But if you were never born, how could you have possibly traveled back in time to commit the act in the first place? The event seems to erase its own cause, creating a devastating logical loop that should make the entire scenario impossible. This is the grandfather paradox in its most classic form, and it has been the central plot device of countless science fiction stories because it so perfectly encapsulates the terrifying logical consequences of meddling with the past. This paradox isn't just a fun narrative trick. It highlights a genuine and serious tension within our best physical theories. Einstein's general relativity allows for the existence of solutions to its equations known as closed time-like curves, paths through the warped geometry of spacetime that could, in theory, loop back into the past. The math doesn't explicitly forbid it, yet the grandfather paradox suggests that if such time travel were possible, the universe would be plagued by logical inconsistencies that violate fundamental rules of cause and effect. It forces physicists and philosophers to propose mechanisms that would prevent such contradictions from ever actually occurring in reality. One compelling solution is the principle of self-consistency, often associated with physicist Igor Novikov. This idea suggests that the timeline is immutable and fixed. Any attempt to change the past would inevitably fail, not through some external force, but through a seemingly endless series of improbable coincidences that guarantee events unfold exactly as they always have. Your actions in the past were always a part of that past. You might travel back with the intention of stopping your grandfather, but something would always prevent you from succeeding: a sudden slip, a missed bus, a change of heart at the last second. The universe, in this view, is a single, consistent story where every event is locked in place, and time travel would simply be a mechanism for playing out your predetermined role in that story, not for rewriting it. A second, and even more mind-bending, solution comes from the many worlds interpretation of quantum mechanics. In this framework, the paradox simply evaporates because there is no single, mutable timeline to create a contradiction in the first place. The moment you arrive in the past and interact with it, your actions cause the timeline to branch into a new, parallel universe. In this new branch, you do indeed prevent your grandfather from meeting your grandmother. This means that in this new reality, the version of you that traveled back in time is never born. However, that doesn't erase the you who is already there. You are a visitor from the original branch, and your existence is independent of the new history you are creating. The original timeline where you were born remains untouched and unchanged. You haven't erased yourself. You've simply created a new parallel universe where a different future unfolds, one that does not include your lineage. This solution preserves free will and allows for change, but at the cost of creating an infinite multiverse where every possible action spawns a new reality. The grandfather paradox ultimately forces us to confront two of the most profound questions about the nature of reality. First, is the past fixed or mutable? Is history a single, unchangeable film reel, or a fluid narrative that can be rewritten? The self-consistency model argues for a block universe where all of time exists simultaneously, and our perception of moving through it is an illusion. The many worlds model offers a more dynamic, albeit chaotic, vision where the past is as fluid as the future. Second, and perhaps more personally, does this mean free will is an illusion? If the timeline is fixed and your actions in the past were always destined to happen, then your feeling of making choices is just that, a feeling. Your path was set from the beginning. Even the many worlds interpretation presents a strange form of destiny. Every possible choice you could make will be made in some branch of the multiverse. You don't choose the branch, you simply become aware of the one you're on. This paradox, born from a simple time travel story, becomes a gateway to questioning the very fabric of causality, identity, and our ability to shape our own destiny. It remains a powerful tool, not for proving time travel is impossible, but for helping us understand what time itself actually is. If the idea of self-aware simulations wasn't strange enough, our next paradox takes the concept of a disembodied mind to its most extreme and unsettling conclusion, born not from advanced technology, but from the relentless, random churn of atoms over an infinite amount of time. This is the Boltzmann brain paradox, a thought experiment so bizarre that it seems like science fiction, yet it emerges directly from the laws of thermodynamics and our current models of the cosmos. It's named for the 19th century physicist Ludwig Boltzmann, who helped develop our modern understanding of entropy, the idea that disorder in a closed system always increases. But he also recognized that in a system with truly infinite time, even the most wildly improbable events are not just possible, they are inevitable. Given enough time, a room full of gas molecules randomly bouncing around will, by pure chance, suddenly and momentarily arrange themselves into a complex and ordered shape. The air in your room could, in theory, spontaneously form a perfect ice sculpture or a detailed cloud of smoke that looks exactly like a face. It's incredibly unlikely, but over eternity it will happen. Now take this principle and apply it to the entire universe. If the cosmos is eternal and mostly empty, as a heat-death scenario suggests, then over mind-numbingly vast eons, the random quantum fluctuations in the void could theoretically assemble something far more complex than a smoke signal face. They could, by sheer accident, assemble a fully formed, self-aware human brain, complete with all the memories, sensations, and thoughts of a living person. This brain would pop into existence, float in the emptiness of space for a fleeting moment, experience a brief, convincing illusion of being a real person living in a real world, and then just as quickly dissolve back into the chaotic vacuum. It wouldn't be attached to a body, it wouldn't have evolved. It would be a cosmic accident, a momentary glitch in the silence of eternity that mistakenly believes it is something more. This leads to the deeply disturbing core of the paradox. If our current cosmological models are correct and the universe is destined for an eternal, empty, high-entropy state, then the number of these random, disembodied Boltzmann brains fluctuating into existence over infinite time should be unimaginably larger than the number of actual, evolved beings like us who formed through billions of years of biological evolution. The odds, therefore, would overwhelmingly suggest that you and I are not the products of a long, structured cosmic and biological history. We are far more likely to be one of these temporary, accidental brains, experiencing a brief and utterly convincing hallucination of a universe that doesn't actually exist. Your feeling that you are reading this right now, your memories, your sense of a past and a future, all of it would be nothing more than a random, meaningless flicker in an endless, dark sea of nothingness. This isn't just a quirky puzzle. It's a devastating critique that physicists use to test the validity of our cosmological theories. A theory that predicts your own consciousness is most probably an illusion, is considered by many to be a theory in serious trouble. The Boltzmann brain paradox acts as a kind of philosophical reductio ad absurdum, forcing scientists to refine their models to avoid this bizarre conclusion. For instance, if the universe is not eternal but has a definite beginning and end, or if the vacuum energy of dark energy decays over time, preventing true eternity, then the time available for these random fluctuations is limited, making the spontaneous formation of a complex brain so improbable that it can be effectively ruled out. The paradox, therefore, isn't a suggestion that we are actually Boltzmann brains, but a powerful logical tool that pushes us toward a more accurate picture of the universe's origin and ultimate fate. It tells us that our cosmos likely isn't a static, eternal void, but a dynamic system with a specific history and trajectory that prevents such absurdities from being likely. It's a profound reminder that our grasp on reality is built on the foundation of our best theories, and sometimes the strangest thought experiments are the ones that keep those theories honest. Now, let's venture into one of the most personally unsettling and existentially dizzying ideas on our list, a paradox that takes the many worlds interpretation of quantum mechanics to its most extreme and intimate conclusion. This is the quantum immortality paradox, and it doesn't just ask what happens to the universe when choices are made. It asks what happens to you. According to the many worlds theory, first proposed by Hugh Everett in the 1950s, every time a quantum event occurs with more than one possible outcome, the entire universe doesn't choose one path. Instead, it splits into multiple branches, each one realizing a different possibility. Every flip of a coin, every random decay of a particle, creates a new parallel reality. In this vast, ever-branching multiverse, every possible event that can happen does happen somewhere. Apply this relentless branching to the most significant event any conscious being will ever face: death. Imagine you are in a situation where death seems almost certain. Perhaps you're in a plane that's about to crash, or you're facing a fatal illness, or even playing a truly deadly game of Russian roulette with a revolver. In our classical single-universe view, the outcome is binary. You either survive or you don't. But the many worlds interpretation suggests a third, far stranger possibility. At the moment of the potentially fatal event, the universe splits. In one branch, the random quantum events align in the worst possible way. The bullet fires, the plane impacts, the illness progresses, and that version of you dies. But in another, nearly identical branch, a different quantum fluctuation occurs. The gun's firing mechanism jams due to a random atomic defect. A sudden, unexpected gust of wind alters the plane's trajectory just enough. A spontaneous remission begins. In that branch, you survive against all odds. The shocking implication of the quantum immortality paradox is that from your own first-person, subjective perspective, you will always find yourself in one of the branches where you survived. You will never experience the moment of your own death because in the branches where death occurs, your consciousness ceases. You are not around to observe that outcome. From your point of view, no matter how low the odds of survival might be in a single universe, you will continually experience a sequence of increasingly improbable near misses throughout your life. You would effectively have the illusion of immortality, a life that seems charmed, constantly cheating death through a never-ending string of miraculous flukes and lucky breaks. Your conscious experience would never include the finality of death. It would just seem to go on and on. This idea immediately plunges us into deep philosophical waters, starting with the nature of identity. If you are the stream of consciousness experiencing this sequence of survival branches, what happens to the you in the branches where death occurs? Are they still you? The theory suggests that from a God's eye view of the multiverse, most versions of you do indeed die, often young and tragically. But your specific subjective experience is tied only to the timeline where you continue to exist. This leads to the unsettling question of whether you are incredibly special or utterly insignificant. You feel special because you keep surviving, but in reality, you are just one thread of consciousness in an infinite tapestry of versions, most of whom are not so fortunate. Critics of this idea point out several major flaws. The first is a matter of probability. While your consciousness might follow a path of survival, the quality of that survival could rapidly deteriorate. You might survive a car crash but be left with severe, life-altering brain damage. In the next deadly scenario, the branch where you survive might leave you in a persistent vegetative state. The theory doesn't guarantee a healthy, continuous consciousness, just a continuous biological existence of some kind. Eventually, after enough brushes with death, the only branches left where you are still technically alive might be ones where you have no meaningful consciousness at all, trapped in a broken body, which is a fate arguably worse than death. Furthermore, this paradox heavily relies on the assumption that consciousness is a fundamental, unbreakable thread that can seamlessly jump between branches, which is not a claim supported by neuroscience. Our sense of self is tightly bound to a specific, continuous brain process in a single body. The idea that you would subjectively experience hopping between universes is a dramatic interpretation that many physicists and philosophers find to be a misapplication of the many worlds theory, conflating the mathematics of quantum mechanics with a very specific and untestable hypothesis about personal identity. Despite these criticisms, the quantum immortality paradox remains a profoundly provocative thought experiment. It forces us to confront our own mortality not with data, but with a dizzying alternative. It challenges the very finality of death, suggesting that in some bizarre sense, the show might always go on for the observer. It merges the cold, mathematical logic of parallel universes with the warm, terrifyingly personal fear of oblivion, creating a concept that is as haunting as it is fascinating. It ultimately leaves us wondering whether our existence is a single, fragile story with a definitive ending, or whether we are eternal witnesses in a multiverse that always, somehow, finds a way to keep the narrative alive. But if the bizarre world of quantum immortality feels almost too personal, our next paradox pulls the lens back out to the grandest scales of the cosmos, focusing on the single greatest unsolved mystery in modern astronomy, the enigma of dark matter. The evidence for its existence is absolutely overwhelming, etched into the very fabric of the universe itself. When astronomers measure how fast stars orbit the center of their galaxies, they find something astonishing. According to the laws of gravity, stars on the outer edges of a spiral galaxy should be moving much more slowly than those near the center, just as Pluto orbits our Sun far more sluggishly than Mercury. But that's not what we see. Stars at the edge of a galaxy whip around at nearly the same speed as those close in, as if the entire galaxy is a solid disk. The only way this makes sense is if the galaxy is surrounded by an enormous, massive halo of something that doesn't emit or absorb any light, but whose immense gravitational pull is the only thing keeping these fast-moving stars from flying off into intergalactic space. This invisible gravitational glue is what we call dark matter. The proof doesn't stop there. When we look at giant clusters of galaxies, we see the same story. The galaxies within these clusters are moving so rapidly that the clusters should have torn themselves apart long ago, unless they are held together by the gravity of far more mass than we can see. We can even watch the light from distant galaxies as it travels past these massive clusters. The invisible mass warps the fabric of space-time so dramatically that it acts like a colossal lens, bending the light and creating distorted, stretched images of the background galaxies in a phenomenon known as gravitational lensing. By measuring this distortion, we can literally map the distribution of the unseen mass, and the conclusion is always the same. What we see, all the stars, gas, and planets, is just the visible frosting on a much larger, invisible cake. Dark matter outweighs normal matter by a ratio of about 5:1. It is the universe's primary building block, the hidden scaffolding upon which the cosmic web of galaxies is built. For decades, the leading hypothesis has been that dark matter must be made of some kind of exotic, undiscovered particle that doesn't interact with light or ordinary matter except through gravity. The prime candidate for years has been the WIMP, or weakly interacting massive particle. These hypothetical particles would be heavy and slow-moving, and they would only rarely bump into normal matter through the weak nuclear force, making them incredibly difficult to catch. To find them, physicists have built exquisitely sensitive detectors and placed them deep underground in abandoned mines and tunnels, shielding them from cosmic rays and other background noise. These experiments have been running for years, growing larger and more sensitive with each iteration. And yet, despite this monumental effort, not a single definitive, direct detection of a WIMP has been made. The detectors remain silent. This persistent silence has led to a growing and passionate debate within the scientific community, giving rise to a fascinating alternative. What if we're looking for a particle that doesn't exist? What if, instead of an invisible substance, the effects we attribute to dark matter are actually telling us that our understanding of gravity itself is incomplete? This is the premise of modified Newtonian dynamics, or MUND, proposed by physicist Mordechai Milgrom in the 1980s. MUND suggests that Newton's famous law of gravity breaks down at extremely low accelerations, like those experienced at the edges of galaxies. It proposes a tiny tweak to the equations, a new constant that kicks in when gravitational forces become incredibly weak. Remarkably, this simple modification can accurately predict the rotation curves of many galaxies without invoking any unseen matter at all. For its proponents, MUND is an elegant solution that does away with the need for a mysterious, undetectable particle that has eluded us for 50 years. However, MUND faces its own monumental challenges. While it works beautifully for explaining the motions within individual galaxies, it struggles to account for all the evidence on larger scales. Observations of colliding galaxy clusters, like the famous Bullet Cluster, provide what many consider to be a knockout blow for modified gravity. In these cosmic collisions, the visible gas clouds smash into each other and slow down, but the majority of the mass, as mapped by gravitational lensing, seems to have sailed right through the collision, completely separate from the visible matter. This is exactly what you would expect if the mass were made of collisionless, weakly interacting dark matter particles, but it is incredibly difficult for any modification of gravity to explain how gravity could become separated from the visible mass that supposedly sources it. The bullet cluster seems to show us that dark matter is not just a mathematical fix. It behaves like a real, physical substance that can be pulled apart from normal matter. Faced with this stalemate, the search has expanded beyond WIMP. Other promising particle candidates have entered the spotlight, most notably the action. This hypothetical particle was originally proposed to solve a completely different problem in particle physics, but has since become a leading dark matter contender. Actions would be billions of times lighter than WIMP, behaving less like individual particles and more like a pervasive, rippling wave throughout the cosmos. Detecting them requires a whole new suite of experiments that look not for a nuclear recoil, but for the action's subtle conversion into photons in the presence of a powerful magnetic field. Other theories propose that dark matter isn't a single particle but a whole hidden sector of particles with its own rich physics, or even primordial black holes left over from the universe's first moments. The dark matter paradox, therefore, is not just a simple question of what something is made of. It represents a profound crossroads in our understanding of physics. Do we double down on the search for particles, trusting that our experiments will eventually find what the cosmos so clearly implies is there? Or do we have the courage to reconsider one of the most fundamental and successful laws of physics, gravity, that has guided us since Newton? This isn't a purely academic debate. The answer will redefine our place in the universe. Discovering a dark matter particle would open a window into a whole new world of physics, a shadow universe operating in parallel to our own. Proving modified gravity correct would be a revolution on par with Einstein's overthrow of Newton, forcing a rewrite of the textbooks on how the cosmos actually holds itself together. The paradox forces a humility upon us, reminding that the universe is under no obligation to conform to our expectations, and that the most dominant component of reality might be the one that is forever just beyond our grasp. Now let's push the boundaries of reality even further by considering a paradox that questions the very nature of what we consider real, the Unruh effect. Imagine two astronauts floating in what appears to be the deepest, darkest, most perfect vacuum of space. To one astronaut who is drifting completely motionless, this void feels exactly as it looks, utterly empty, silent, and cold. There is nothing there, but now imagine the second astronaut suddenly fires up a rocket pack and begins accelerating, constantly gaining speed. For this astronaut, something miraculous and bizarre happens. Their surroundings are no longer empty. Their sensitive instruments begin to detect a faint bath of warm particles, real, measurable particles filling the space around them. They even feel a gentle heat. From the perspective of the accelerating observer, the vacuum has somehow come alive. This is the Unruh effect, a stunning prediction of quantum field theory that tells us the very concept of a particle is not universal, but depends entirely on your state of motion. This isn't some abstract mathematical trick. It's a direct consequence of marrying Einstein's theory of special relativity with quantum mechanics. In quantum field theory, what we call empty space isn't really empty. It's a seething, vibrant arena known as the quantum vacuum, where pairs of virtual particles and antiparticles are constantly flickering into and out of existence, borrowing energy from nothingness for a fleeting moment before annihilating and paying the debt back. For an inertial observer, someone moving at a constant velocity, these fluctuations average out to zero. They cancel each other perfectly, and the vacuum appears perfectly quiet and empty. But for an accelerating observer, this delicate balance is disrupted. Their acceleration acts like a kind of horizon, similar to the event horizon of a black hole, which prevents them from seeing the full picture of the quantum foam. This distorted view means those virtual particles no longer perfectly cancel out. Some of them get promoted from virtual to real, appearing to the accelerating astronaut as a real thermal bath of particles, with a temperature directly proportional to their acceleration. The harder they accelerate, the hotter this phantom glow becomes. The profound paradox here is that both astronauts are correct in their observations. There is no single objective answer to the question, is this space empty? The vacuum has no absolute properties. What one observer experiences as a true nothingness, another experiences as a warm somethingness teeming with particles. This forces us to abandon the classical idea that particles are little hard balls that exist independently in the world. Instead, particles are more like excitations or patterns in underlying quantum fields, and whether or not those patterns are activated into a detectable state depends on the path an observer takes through spacetime. It blurs the line between something and nothing to the point of meaninglessness, suggesting that existence itself is a relative concept defined by the observer's motion. This discovery, made by physicist Bill Unruh in 1976, is far more than a curiosity. It is deeply connected to one of the most famous phenomena in all of physics, Hawking radiation. Just as an accelerating observer can't see the full quantum vacuum and thus detects particles, an observer outside a black hole can't see the full vacuum because the event horizon gets in the way. Stephen Hawking realized this distortion would cause a black hole to radiate particles with a thermal spectrum, slowly losing mass. The Unruh effect provides a simpler, more accessible analogy for understanding this otherwise baffling process. It's Hawking radiation for acceleration instead of gravity. Both effects point to a deep and mysterious connection between acceleration, gravity, and thermodynamics, suggesting that heat, entropy, and information are somehow woven into the fabric of spacetime itself. Ultimately, the Unruh effect paradox shatters our comfortable illusions about the emptiness of space. It reveals a universe that is fundamentally restless and alive with potentiality, a cosmic stage where the actors, the particles, only appear when an audience member, the observer, takes a specific accelerating seat. It tells us that the cold, dark void is an illusion of our inertial perspective, and that if we were to move through it with enough purpose, we would find ourselves swimming in a sea of warmth and light, a phantom reality made tangible only by our own journey through the cosmos. Now let's shift our focus from the vast and energetic to the seemingly simple and mundane, with a paradox that begins with a single grain of sand. Imagine a small pile of sand on a beach. It's clearly a heap. Now, remove one single grain. Is it still a heap? Of course it is. Remove another grain and another. At what precise grain does this collection of sand cease to be a heap and become something else, a scattering or just a few grains? There is no clear line, no definitive moment of transition. This is the classic Fermi Paradox, a logical puzzle that has perplexed philosophers since ancient times, and it derives its name from the Greek word soros, meaning heap. It highlights the problem of vagueness, showing how our everyday language and concepts often break down when we try to apply strict, binary boundaries to things that exist on a spectrum. Now take this ancient thought experiment and apply it to the grandest concept of all, the entire universe. If we consider the universe to be the sum total of all matter, energy, space, and time, what happens if we begin to subtract from it? If we remove one single atom from the cosmos, is it still the universe? Intuitively, yes. Remove another and another. If we continue this process atom by atom, planet by planet, galaxy by galaxy, at what exact point does the universe cease to be the universe? Does it still qualify as the universe when only our Milky Way remains, when only our solar system is left, or when just one lone hydrogen atom is drifting in the void. This application of the Fermi Paradox to cosmology forces us to confront the unsettling idea that even our most fundamental concepts might be inherently vague, with no clear-cut boundaries to define them. This paradox becomes even more intense when we view it through the lenses of modern physics. In the quantum realm, the very idea of a discrete thing becomes fuzzy. Particles are not tiny billiard balls with definite locations. They are probability clouds, and in the many worlds interpretation of quantum mechanics, the concept of a single, defined universe might be an illusion altogether. Perhaps what we call the universe is just one branch of a near-infinite multiverse, a single thread in a vast cosmic tapestry. In that context, the paradox asks, if a branching event creates a new universe that is almost identical to ours, differing by just one quantum event, is it a separate universe or still part of the original? How many changes does it take before it becomes something entirely other? The boundaries between one universe and another, or between a universe and the multiverse, might be just as vague as the boundary between a heap and a non-heap of sand. This line of thinking pushes us into the domain of ontology, the philosophical study of the nature of being and existence. It challenges the comforting assumption that the categories we use to describe reality are solid and reliable. We like to think that a chair is a chair, a planet is a planet, and the universe is the universe, but the Fermi Paradox suggests that these categories are human constructions, useful for navigating the world but potentially misleading when we try to understand the universe's true, fundamental nature. It encourages us to consider whether reality is ultimately discrete, made of individual bits like atoms or pixels, or whether it is a seamless, continuous whole where any division we impose is arbitrary. This isn't just an academic word game. It has implications for how we model the cosmos in physics and cosmology, forcing us to question whether our mathematical descriptions capture reality or merely our limited, granular perception of it. Ultimately, this paradox serves as a profound reminder of the limits of human language and cognition when faced with the sheer complexity and scale of existence. It invites a deep humility, suggesting that the universe might not conform to our desire for neat, clean categories. The boundaries we draw between object and environment, between self and other, and even between one universe and the next, might be useful fictions rather than absolute truths. Embracing this inherent fuzziness isn't a surrender to confusion. It's an invitation to a more nuanced and flexible understanding of reality, one where questions are often more valuable than definitive answers, and where the journey of inquiry itself reveals the stunning, layered complexity of the cosmos we call home. But if the Unruh effect challenges what we consider real, and the Fermi Paradox questions the boundaries of existence, our next enigma confronts the most fundamental question of all: why is there something rather than nothing? To answer that, we must rewind the cosmic clock back to the very first moments after the Big Bang, a period of unimaginable energy and density. According to our best theories of particle physics, the universe in its fiery infancy should have created matter and antimatter in a state of perfect symmetry. For every quark born, an antiquark should have been its twin, for every electron a positron. These particles and antiparticles are identical in almost every way, except for their opposite electrical charges. And when a particle meets its antiparticle, they annihilate each other in a brilliant flash of pure energy, returning to the void from which they came. If this perfect symmetry had held, the story of the universe would have been incredibly brief and utterly empty. All the particles and antiparticles would have mutually annihilated, leaving behind a vast, featureless sea of radiation, a cosmos of light with no stars, no planets, and no possibility of life. The fact that you and I are here to ponder this means that this perfect balance was broken. Somehow, for every billion pairs of matter and antimatter that annihilated in the early universe, a tiny surplus of matter, about one single particle, was left over. That 1 in a billion imbalance is all we are. Every atom in your body, every star in the sky, every structure we see is made from that minuscule leftover residue from a near-total cancellation. This is the Barrian asymmetry paradox, and it asks the simple, devastating question: why did this tiny excess of matter exist at all? The hunt for an answer leads us deep into the world of particle accelerators like the Large Hadron Collider, where physicists are trying to recreate the conditions of the early universe to find the mechanism that tipped the scales. The current best hope lies in a phenomenon known as CP violation. CP stands for charge and parity. It means that the laws of physics might treat particles and their mirror image antiparticles slightly differently. Imagine a left-handed particle and a right-handed antiparticle. If the universe is perfectly symmetric, they should behave in exactly the same way. But if CP violation occurs, they would decay at slightly different rates. This tiny difference in behavior could, over time, lead to the small surplus of matter we see today. We know that CP violation is real because we've observed it in the behavior of certain exotic particles called mesons. However, the amount of CP violation measured in these experiments is far too small to account for the vast amount of matter we see in the universe. It's like finding a single dropped coin when you need to explain the existence of all the world's treasuries. This means our current standard model of particle physics is incomplete. There must be other, much stronger sources of CP violation out there, coming from new particles or forces that we haven't discovered yet. This paradox is therefore a direct beacon pointing toward physics beyond the standard model. Other theories propose even more dramatic scenarios. One compelling idea is that of leptogenesis. This suggests that the initial asymmetry didn't start in the matter we're familiar with, but in ghostly particles called neutrinos. Heavy, right-handed neutrinos, which are predicted by some theories but have not yet been found, could have decayed asymmetrically in the early universe, creating a slight preference for matter over antimatter. This initial bias would then have been communicated through interactions to the rest of the particle world, eventually seeding the cosmos with the matter that would form everything we see. Another possibility involves processes that occurred during the inflationary period of the universe, where quantum fluctuations were stretched to cosmic sizes, potentially locking in a matter-antimatter imbalance across the entire cosmos. The profound weight of this paradox cannot be overstated. It is not merely a technical detail of particle physics, it is the central plot point in the story of our existence. The quest to solve it is a quest to understand our own origins. It reveals a universe that is not perfectly symmetrical and sterile, but one that is slightly flawed, slightly biased, and beautifully lopsided in just the right way to allow for complexity, consciousness, and wonder. The existence of everything from the grandest galaxy to the smallest thought hinges on a subtle crack in the mirror of reality, a tiny imperfection in the laws of physics that made all the difference. Just as we ponder the lopsided genesis of matter, another profound puzzle emerges from the earliest moments of the cosmos, one that challenges our understanding of how the universe could possibly be so uniform. Look up at the night sky in any direction you choose, and with powerful telescopes, you'll see something truly remarkable. The temperature of the cosmic microwave background radiation, the ancient afterglow of the Big Bang, is almost exactly the same everywhere. To be precise, it's uniform to within 1 part in 100,000. This incredible consistency is a cornerstone of our modern cosmological model, but it also presents a devastating logical problem. According to the standard Big Bang theory, there simply hasn't been enough time since the beginning of the universe for these vastly separated regions to have ever communicated with each other to achieve this thermal equilibrium. Think of it like this. Imagine you walk into a vast concert hall and find that every single seat is set to the exact same, perfectly comfortable temperature. You would naturally assume the hall has a central heating and cooling system that has been running long enough to evenly distribute the air. Now, imagine you're told the hall was built just 1 minute ago and there is no central system. The perfect temperature uniformity suddenly becomes inexplicable. This is the essence of the horizon problem. The universe we observe has regions that are separated by billions of light years. Since nothing can travel faster than light, there is a cosmic horizon, a maximum distance that any signal, including heat, could have traveled since the Big Bang. Two regions on opposite sides of the observable universe are far outside each other's horizons. They are like two isolated islands that have never been connected by a bridge or a boat. By all rights, they should have had no way to share energy and reach the same temperature. They should be as different as random, independent entities can be, yet they are virtually identical. This seems to demand some form of faster-than-light influence in the ancient past, a concept that violates the very foundations of Einstein's relativity. This glaring inconsistency was the primary motivation for one of the most important and successful additions to the Big Bang theory, cosmic inflation. Proposed in the early 1980s by physicists like Alan Guth and Andre Linde, inflation posits that the universe underwent a period of exponentially rapid expansion in the first tiny fraction of a second of its existence. We're talking about a timescale of around 10 to the power of -36 seconds. In that incomprehensibly brief moment, the fabric of spacetime itself is thought to have ballooned by a factor of at least 10 to the power of 26. To put that in perspective, it's like expanding a single atom to the size of an entire galaxy, virtually instantly. This idea elegantly solves the horizon problem. Before inflation, the entire observable universe was crammed into a tiny, subatomic volume that was small enough for every part to be in causal contact. It was all one single, connected neighborhood where energy could be freely exchanged, allowing it to smooth itself out into a uniform temperature. Then, inflation acted like a cosmic zoom lens, taking that tiny, homogeneous patch and stretching it to encompass everything we can see today. The regions that now appear separated by insurmountable horizons were once cozy neighbors, explaining their perfect thermal agreement without needing any faster-than-light communication. However, while inflation provides a beautifully elegant solution, it also introduces its own set of deep mysteries and amplifies the problem of fine-tuning. The theory requires that the inflationary field, often called the inflaton, had very specific properties. It needed to have just the right amount of energy to initiate the expansion, and then it needed to turn off at exactly the right moment to gracefully transition into the more sedate expansion of the standard hot Big Bang. If the inflation had lasted a fraction of a second too long, the universe would have been stretched into such a thin, empty void that no galaxies could ever form. If it had ended too soon, the universe would have remained too small and lumpy, never achieving the large-scale uniformity we see. Getting this balance right feels like a cosmic coincidence of staggering precision. This fine-tuning leads some physicists to wonder if inflation is the final answer, or if it is merely a stepping stone to an even deeper theory that will explain why the conditions for inflation were met in the first place. The horizon problem, therefore, is far more than a technical issue about temperature. It is a gateway to the physics of the absolute beginning. It forces us to confront what happened at energies so high that our current theories of particle physics and gravity simply break down. It pushes us toward the need for a theory of quantum gravity, a framework that can describe the behavior of spacetime itself when it was crumpled into a quantum foam. Concepts like string theory, loop quantum gravity, or the idea of a quantum bounce from a previous universe are all attempts to peer behind the curtain of inflation to understand what could have sparked such a monumental event. The Horizon problem reminds us that our cosmic history is still missing its very first chapter, and that the stunning uniformity of the heavens is not a dull fact, but a brilliant clue pointing toward the wild physics of creation. Just when we thought the quantum world couldn't get any stranger, it presents us with an experiment so mind-bending that it seems to unravel the very sequence of time itself. This is the quantum eraser paradox, and it begins with a sophisticated twist on the classic double-slit experiment we discussed earlier. You'll recall that when we send particles like photons or electrons through two slits without watching, they create an interference pattern acting like waves. But the moment we place a detector to see which slit each particle goes through, that pattern vanishes and they behave like particles. This is bizarre enough, but the quantum eraser takes this a step further into the realm of the seemingly impossible. What if we could make that choice to measure or not to measure after the particle has already passed through the slits? What if we could decide its past behavior from the future? This is precisely what delayed choice experiments explore. Here's how a typical version works. Scientists send a particle toward the double slits, but just beyond the slits, they place a special crystal that splits each incoming photon into two entangled photons, what we call a signal photon and an idler photon. The signal photon continues onto the main detector screen, where it will eventually be recorded. Its entangled twin, the idler photon, is sent on a much longer path, a detour that takes it to a separate set of detectors. Crucially, because these two photons are entangled, whatever happens to one instantly influences the other, no matter the distance between them. The truly revolutionary part is the choice we make at the end of the idler photon's path. We can choose to measure which path it took, which instantly forces its entangled signal photon to have taken a definite path, destroying any interference pattern. Or we can choose to erase that which path information by mixing the idler photon's paths together with another device, which forces the signal photon to have behaved like a wave, creating an interference pattern. The staggering conclusion is that this choice, to erase or not erase the information, is made after the signal photon has already hit the final detector and its fate has been seemingly decided. It's as if our actions in the present are reaching backwards in time to rewrite the history of what the particle did in the past. This isn't just a theoretical idea. It has been confirmed in laboratories multiple times since the concept was first proposed by physicist John Wheeler in the 1970s and 80s. The results are unambiguous. When the experiment is set up to erase the which path information of the idler photon, an interference pattern magically appears in the data from the signal photons, even though those signal photons were detected before the erasure decision was made. Conversely, when the which path information is allowed to be measured, the interference pattern vanishes. The data itself shows that the past behavior of the particles is not fixed until a future measurement defines it. This creates the profound paradox. The future appears to be influencing the past, challenging our most fundamental assumption about causality, that cause must always precede effect. This has led some physicists to seriously consider interpretations that involve retrocausality, the idea that influences can travel backwards in time. In this view, the measurement choice at the end of the experiment sends a signal backwards along the timeline, telling the particle how it should have behaved when it went through the slits. This isn't time travel in the science fiction sense of sending a person back, but rather a subtle, quantum-level handshake between the past and future that defines the properties of a particle in a consistent loop. Other physicists argue that retrocausality is an illusion caused by our stubborn insistence on seeing time as a linear sequence. They propose that from a God's eye view outside of time, the entire experiment, the emission, the slits, and the final detection, is a single, unified event. In this block universe model, all of time exists simultaneously, and the idea of before and after is just a perspective experienced by conscious beings within the timeline. The particle doesn't have a definite past that gets changed. Its past and future are inextricably linked parts of a whole, and it's only our limited perception that forces us to see it as a sequence. The quantum eraser paradox ultimately forces a dramatic rethink of time, causality, and reality itself. It suggests that the universe at its most fundamental level might not operate like a chain of dominoes falling in a straight line. Instead, it might be more like a vast, interconnected web where every event influences every other event, and the distinctions between past, present, and future are far more fluid than our everyday experience would ever suggest. It reveals a cosmos where reality is not a pre-recorded film but an interactive story still being written, where the questions we ask don't just reveal the answers, they actively participate in creating them. While the quantum eraser plays with the sequence of cause and effect, our next paradox brings us back to a seemingly simple question with profound implications. Why do magnets always have two poles? Break a bar magnet in half and you don't get an isolated north and an isolated south. Instead, you get two smaller magnets, each with its own north and south pole. This is a fundamental feature of electromagnetism as described by James Clerk Maxwell's elegant equations. They are beautifully symmetrical in almost every way, but this symmetry has a glaring hole. For electric charges, we have positive and negative particles that can exist completely independently. Think of a solitary electron or proton. But for magnetism, we only ever find dipoles. This asymmetry has bothered physicists for generations, leading to a powerful prediction. Somewhere out there, there should exist a magnetic monopole, a particle that is just a pure north or pure south magnetic pole. This isn't just a whimsical idea. The existence of magnetic monopoles is a direct prediction of grand unified theories, or GUT. These are ambitious theoretical frameworks that aim to merge the electromagnetic force, the weak nuclear force, and the strong nuclear force into a single, fundamental force. We know that at the incredibly high energies present in the first moments after the Big Bang, these forces were indeed unified. As the universe expanded and cooled, this single force is thought to have undergone a series of phase transitions, much like steam condensing into water, which broke the perfect symmetry and gave us the three distinct forces we see today. The physics of these phase transitions almost inevitably creates topological defects in the fabric of spacetime itself. One such defect would be an incredibly massive, stable particle carrying a single magnetic charge, a magnetic monopole. According to these theories, the early universe should have been flooded with these exotic particles, and they should be as common as protons are today, saturating the cosmos with their unique signature. Yet, when we look, we find nothing. Despite decades of meticulous searching with increasingly sensitive detectors, from deep underground labs to experiments mounted on high-altitude balloons and even the International Space Station, not a single confirmed magnetic monopole has ever been found. This complete absence creates the magnetic monopole paradox. Our best theories of particle physics insist they must exist, but our observations of the universe show no trace of them. This isn't a small oversight. It's a direct contradiction that threatened to unravel the entire concept of grand unification in its early days. If the theories were correct, the sheer density and mass of these monopoles would have dramatically altered the evolution of the universe, likely preventing galaxies from ever forming. The fact that we have a universe filled with galaxies is itself powerful evidence that these monopoles are not out there in the numbers predicted. This glaring conflict between theory and observation was a primary driving force behind one of the most important ideas in modern cosmology: cosmic inflation. Physicist Alan Guth, while working on the monopole problem, realized that a period of hyper-fast, exponential expansion in the universe's first fraction of a second could provide an elegant solution. Imagine the monopoles are like bubbles in a glass of soda, formed during the phase transition as the forces separated. Now, imagine that before you can even take a sip, the glass suddenly expands to the size of the entire solar system. Those bubbles would be so incredibly diluted that you'd be lucky to find even one in your entire expanded glass. That's what inflation did. It took the dense, monopole-rich soup of the primordial universe and stretched spacetime itself by an unimaginable factor, diluting the monopoles to such an extremely low density that they become virtually undetectable. The paradox of their absence wasn't a flaw in the theories. It was a clue that pointed toward a previously unknown chapter in cosmic history, a monumental growth spurt that resolved multiple problems at once. The story of the magnetic monopole is a perfect example of how a negative result, the failure to find something, can be just as powerful a driver of scientific progress as a positive discovery. The absence of evidence forced theorists to think bigger and more creatively, leading to the revolutionary paradigm of inflation, which itself then solved other major puzzles like the horizon and flatness problems. It beautifully illustrates the deep and necessary dialogue between particle physics and cosmology. The hunt for a tiny, hypothetical particle guides our understanding of the universe on its very largest scales, and vice versa. The search is far from over. Many experiments continue to look for these elusive particles because finding just one would be a monumental achievement. It would be a direct confirmation of physics at unimaginably high energies, providing concrete evidence for grand unification and offering a stunning glimpse into the universe's first fleeting moments. The magnetic monopole remains a ghost that haunts the edges of our theories, a missing piece that, if found, would complete a beautiful picture of cosmic symmetry. Yet, even as we grapple with the mysteries of dark matter and the nature of observation, we encounter a paradox so vast and so fundamental that it dwarfs all others, representing the single greatest mismatch between prediction and reality in the entire history of science. This is the vacuum catastrophe, and it centers on a concept that seems deceptively simple: the energy of empty space. According to quantum field theory, the vacuum is not a true nothingness. It is a seething, bubbling foam of virtual particles that constantly flicker into and out of existence, borrowing energy from nothing for a fleeting moment before annihilating and paying the debt back. This relentless activity should fill every cubic centimeter of space with a colossal amount of energy, a pressure known as vacuum energy or the cosmological constant. When physicists calculate the expected density of this energy based on the known contributions of all quantum fields, they arrive at a number of staggering proportions. It should be an unimaginably powerful force, one that would have ripped the universe apart in its first moments of existence, preventing any galaxy, star, or planet from ever forming. But when astronomers measure the actual effect of this vacuum energy on the cosmos, they find something utterly baffling. Through observations of distant supernova, the cosmic microwave background, and the large-scale structure of the universe, they have determined that dark energy, the force accelerating the expansion of the cosmos, is real. However, its measured strength is about 120 orders of magnitude smaller than the quantum field theory prediction. To grasp the sheer scale of this error, imagine predicting that a single raindrop contains all the water in all the oceans on Earth, and then going outside with a beaker to measure the raindrop and finding it holds just a single, ordinary drop of water. The discrepancy is not just a minor rounding error. It is a chasm of misunderstanding so deep and so wide that it points to a fundamental flaw in our most successful theories of the very small and the very large. This catastrophic mismatch forces physicists to consider several radical possibilities. The first is that our understanding of quantum field theory is incomplete. Perhaps the contributions of all these virtual particles don't simply add up in a straightforward way. Maybe there is a hidden symmetry or a cancellation mechanism of incredible precision that we have not yet discovered. Supersymmetry, a beloved theory for many particle physicists, offers a potential path. It proposes that every known particle has a super-partner particle. The contributions of these partner particles to the vacuum energy could have opposite signs, cancelling out the enormous predicted value to a very small number. The problem is that even if supersymmetry is real, the cancellation is not perfect enough to get us anywhere near the tiny observed value. Furthermore, we have not yet found any evidence for these superpartner particles at particle colliders, leaving the idea on shaky ground. Another mind-bending proposal is that our universe is not the only one. The concept of the string theory landscape suggests there could be a near-infinite number of parallel universes, each with different physical constants and different values for the vacuum energy. In this vast multiverse, most universes have a cosmological constant so large that they are instantly torn apart or collapse. Only in an exceedingly rare subset of universes, like our own, is the value small enough to allow for the formation of galaxies and life. This is a form of anthropic reasoning. We find ourselves in a universe with a strangely small cosmological constant because it is the only type of universe that can support conscious observers to wonder about it. While this provides a potential explanation, it is deeply unsatisfying to many scientists because it moves the question from why is this number this value? To why do we live in a universe where this number has this value? Essentially replacing one mystery with another. A more radical solution is that we are fundamentally wrong about gravity. Einstein's theory of general relativity, which beautifully describes the force of gravity as the curvature of spacetime, treats the cosmological constant as a free parameter that can be adjusted to fit observations. But what if gravity operates differently on the largest scales? What if our theory of gravity needs a major overhaul to properly account for the energy of the vacuum? And the vacuum catastrophe is the glaring sign pointing toward that revolution. This would mean that the solution lies not in fixing quantum mechanics, but in discovering a new theory of quantum gravity that seamlessly merges the worlds of the very small and the very large, finally explaining why empty space has the weight that it does. The vacuum catastrophe is ultimately a profound lesson in humility. It stands as a monument to the limits of human knowledge, showing us that even our most brilliant and successful theories can contain errors of astronomical proportions when pushed to their extremes. It is not a failure of science, but a beacon, a glaring signpost that we are on the verge of a paradigm shift as monumental as the ones brought about by relativity or quantum mechanics themselves. The void is not empty. It is filled with the deepest question of all, and the answer will likely rewrite our understanding of reality itself. And now we arrive at a paradox that lies at the very heart of quantum theory. a question so fundamental that it has divided physicists for nearly a century. It's not about a specific phenomenon, but about the core mechanism of the theory itself. Quantum mechanics is arguably the most successful and accurate scientific theory ever devised. Its mathematical framework allows us to predict the behavior of particles with breathtaking precision, powering everything from the lasers in your DVD player to the transistors in your phone. The equations work flawlessly, but when we step back from the math and ask a simple, seemingly innocent question, what actually happens when we measure a quantum system, the entire foundation of the theory dissolves into a cloud of profound mystery and fierce debate. This is the measurement problem paradox, and it reveals that for all our computational power, we may not understand the first thing about how the universe actually works at its most basic level. The problem arises from the strange duality at the core of quantum behavior. We have the wave function, a mathematical entity that describes a particle as a smear of probabilities, existing in a superposition of all its possible states. This wave function evolves smoothly and predictably over time according to the Schrödinger equation. Then we have the measurement. The moment we look, the moment we try to pin down a property like position or spin, this fuzzy cloud of possibilities seems to instantly snap into a single, definite reality. A single click on a detector, a single dot on a screen. This sudden transition from the multiple to the single is what we call the collapse of the wave function. The paradox is that this collapse isn't described by the Schrödinger equation itself. It's an entirely separate, ad hoc rule that physicists had to bolt onto the theory to make it match what we actually observe in the lab. The mathematics gives us a world of shimmering potentialities, but our experience is one of concrete facts. The measurement problem is the giant, unanswered question of what connects these two worlds and what exactly triggers this magical, instantaneous collapse. This has led to a spectrum of interpretations, each more mind-bending than the last, and none with a consensus. On one end, we have the Copenhagen interpretation, the traditional textbook answer championed by Niels Bohr and Werner Heisenberg. It essentially draws a line in the sand. It says the quantum world of waves and the classical world of definite objects are separate realms. The wave function isn't a description of reality, but a catalogue of our knowledge. It only collapses when it interacts with a classical measuring device, and the act of measurement is a primitive, irreducible process that we're not meant to understand further. It's a pragmatic approach that says, shut up and calculate, but it leaves the definition of a classical device hopelessly vague. Is it a single atom? A photographic plate, a human eye? Dissatisfaction with this vagueness led to other, wilder ideas. Some, like the pioneering physicist Eugene Wigner, suggested that consciousness itself is the trigger. In this view, it's not the measuring device but the entry of the information into a conscious mind that finally collapses the wave function, placing human awareness at the center of the cosmic story. Most physicists find this idea unpalatable, as it seems to mix the physical and the mental in a way that is utterly untestable. On the opposite extreme is Hugh Everett's many worlds interpretation, which offers a radical solution. It eliminates collapse entirely. Everett said the wave function never collapses. Instead, at the moment of a measurement, the universe itself splits into multiple branches. Every possible outcome actually occurs, but each one plays out in a newly created parallel reality. In one world, the electron went through the left slit. In another, it went through the right. There is no single outcome and therefore no paradox, just an infinite, ever-branching multiverse where every possibility is realized. It's an elegant solution mathematically, but it demands we accept a reality of breathtaking, and some would say wasteful, proportions. Other theories attempt to find a more physical mechanism. Dynamical collapse models propose that the wave function collapse is a real, physical process that happens spontaneously when a system reaches a certain size or complexity. Gravity might be the culprit, providing an objective threshold between the quantum and classical worlds. Then there is the decoherence theory, which doesn't so much solve the problem as explain why we don't see superpositions in everyday life. It shows how a quantum system instantly loses its coherence by interacting with its environment, the air molecules, photons, and other particles around it. This interaction makes the weird quantum effects effectively leak away, making the system appear classical. But critics argue decoherence only explains why we see a single outcome. It doesn't actually explain why that particular outcome was chosen from the many possibilities. It tells us how the illusion is created, but not how the magician performs the trick. The sheer persistence of this paradox, nearly 100 years after the theory's founding, is a stunning testament to the limits of our knowledge. We have a tool of immense power and accuracy, yet we cannot agree on what that tool is actually describing. Is it a world of objective reality waiting to be discovered? Is it a world of relative facts defined by our interactions? Or is it a world of endless possibilities, all equally real? The measurement problem forces us to confront the possibility that reality at its most fundamental level might be ultimately unknowable, that the questions we ask are framed in a language that the universe simply doesn't speak. Or perhaps it is simply waiting for a new Einstein, a new perspective that will reveal the solution to be so elegant and obvious that we will wonder how we ever missed it. Until then, the paradox remains a silent ghost in the most successful machine ever built by science. We've journeyed through 22 paradoxes that stretch the limits of human comprehension, from the haunting silence of alien civilizations to the quantum enigmas that unravel time itself. Each one of these cosmic riddles does more than just expose a gap in our understanding. It shines a light on a doorway, an opportunity for a discovery so profound it could rewrite the laws of physics as we know them. They remind us that the universe is far stranger, more layered, and more wonderfully bizarre than our everyday experience would ever suggest. It doesn't play by the straightforward rules our intuition expects. Instead, it operates on a logic all its own, a deeper set of rules waiting to be decoded. Embracing this uncertainty isn't a sign of scientific failure, it is the very engine of progress. Every great leap in human knowledge began with a paradox that refused to be ignored. The contradictions we've explored are not dead ends, they are invitations. They are the universe's way of pushing us to think bigger, to question deeper, and to imagine wilder possibilities. They demand a humility that is essential for any true explorer, whether you're a physicist working at the edge of theoretical mathematics or someone simply gazing up at the stars filled with wonder. This humility, this acceptance that we don't have all the answers, is what keeps the scientific story alive, dynamic, and endlessly fascinating. As we continue to probe the cosmos, from the vast expanses between galaxies to the frenetic energy of the quantum foam, let these mind-twisting puzzles serve as a constant source of inspiration. Let them fuel your curiosity and ignite conversations about the nature of reality, time, and our own place in this grand, mysterious cosmos. The journey doesn't end here. Each paradox is a starting point, a trailhead leading into even deeper mysteries. We want to hear which of these enigmas resonates most with you, which one keeps you up at night, turning the problem over and over in your mind. Share your thoughts in the comments below. Let's continue this exploration together. And if you're eager to keep unraveling the mysteries of existence with us, make sure to subscribe and hit the notification bell so you never miss our next deep dive into the fabric of reality. The universe is waiting, and its greatest secrets are still hidden, just beyond the next question.